Welcome back to ECE 442-542. This is part D of lecture 6.2. This is now concerned with root locus diagram shape. Why or what determines the shape of the root locus diagram? And we'll basically see this shape by simply varying the gain k from 0 to infinity. The system that we are going to look at, let's say we have a proportional controller, a constant gain k. We are going to adjust that gain k from 0 to infinity and look at what happens to the closed loop poles that result from this particular diagram when g of z, this plant, is 1 over z, z minus 3/2. We can find the closed loop poles from the closed loop transfer function. We know the closed loop poles are determined by the behavior of the denominator, 1 plus kg of z. In terms of the way this system is parameterized, we now have the parameter k, and our system is 1 over z times z minus 1.5. We can obtain a common denominator in the denominator and cancel the common denominator here with that common denominator to end up with the following closed loop transfer function with the denominator a parameterized denominator where the denominator is parameterized by the gain k, where k is now taking on values from 0 to infinity. We want to now know what happens to the roots of this quadratic equation as k changes from 0 all the way up to infinity. The closed loop poles are governed by the denominator, 1 plus kg of z. The numerator of 1 plus kg of z is what we have calculated here, and that ends up being that particular expression. So the numerator of the denominator is going to give rise to z times z minus 1.5 plus k. That's now distributing the z squared minus 1.5 z plus k. We want to follow the roots of that as k varies from 0 to infinity. Hopefully you can see that when k is equal to 0, the roots are given by the values of z that cause this expression to be 0. Meaning at k equal to 0, we better start our root locus at the origin, z equals 0, and z equal 1.5. And that's what this table is telling us, that when k is equal to 0, the two roots, z sub 1 and z sub 2, z1, let's say, is 0, z sub 2 is 3/2. That's where these poles are located in the z-plane. And now we're trying to figure out, how does this red diagram, the root locus diagram, why do we know that it in fact does exist between 0 and 1.5, and the two branches meet halfway between those two poles? We just have two poles in this system. The system is 1 over z, z minus 1.5, no finite zeros. The root locus begins on the poles, and it's going to terminate or approach the infinite zeros, the zeros at infinity, and there's two of those. And as we will see, as we adjust k from 0 up to infinity, here we're not even going to have to go that far. We can step through different values of k and follow those symbols along these branches of the root locus. We have two branches. We start at the poles, the x's. The first, let's say, gain that we use is 1/4. That's the square. When the gain k, and think of k in this expression as an adjustable knob, and we're turning that knob from 0 all the way up to infinity. At a value of 0, we have 0 and 1.5. When we crank the knob up to 0.25 or 1/4, one pole ends up being almost at 0.2, and the other pole has moved down to 1.31 from 1.5. So our poles are approaching each other as we adjust the gain k from 0 to 1/4. When k is equal to 1/2, we end up at the triangles. When k is equal to 1/2, we end up with roots of this expression. When k is equal to 1/2, now we end up with one of those roots at 1/2 and the other root at 1. The poles, or the closed loop poles, which are given by this red locus pattern, are now moving from where they started on the real line. One's going right, one's going left. At the upside down triangle, when the gain is 9/16, they're two real roots at 3/4. So we're halfway between 0 and 1.5 when the gain is 9/16. When we adjust the gain more than 9/16, the poles do not stay on the real axis. They actually separate, and now they maintain the real value of 0.75, but now they start to become complex, or have the complex part of 0.43 and minus j 0.43, and that's this diamond shape. At the star, the gain k is 1. Again, the real value has not changed. It's still 3/4, and the imaginary part is, well, we can actually compute that. We know that at the star, in this particular case, we could find what is the value of that point that intersects the unit circle and has a real value of 3/4. We know that that's a right triangle. We know the real part is 3/4. The imaginary part is y squared, and that's equal to the radius squared, which is 1. We have a squared plus b squared is equal to c squared. C is 1, a is 3/4, b is the y. We can now solve that for y, or y squared to begin with, and now we have 1 minus 9/16. And as we then find, y is the square root of 7/16, or the square root of 7/4. And that should give rise to this plus or minus 0.661. We could have done that even with a calculator. We could do the complex zeros. Here's our parameterized closed loop pole polynomial of z squared minus 1.5z plus k. Vertical line says evaluate that expression when k is equal to 0.25 and solve for the values of z that make that expression 0, and these are allowing for complex zeros to happen, and that's where these points come from. The unfortunate thing with the calculator is that sometimes if you have repeated roots, it will just show you the one value that those two roots are repeated at. But in this case, when k is equal to 9/16, you end up with two roots at 0.75. And now these particular values of k, 0.25, 0.5, 9/16, 3/4, and 1, give rise to the values that we had in this table, and it gives rise to these symbols that are shown to illustrate the progression of the closed loop poles as k is increased. Hopefully you can see then that k needs to be made, let me change colors, k has to be larger than the k to get us to the first triangle, and that means k is going to have to be bigger than 1/2 to get both branches simultaneously inside the unit circle. And k cannot exceed the value of k to get us beyond the unit circle, because once we continue to crank up the gain k beyond that value, we will go unstable. The k then, to yield stability in this case, is going to be between 1 and 1/2. That will then allow us closed loop stability as long as k is between 1/2 and 1. And we verified that actually with a calculator. We could have this root locus sketched in MATLAB, and we'll get to that subsequently.